Welcome back, and thank you very much for watching this lecture video. And in this lecture, we're going to go through some chemical reactions of alcohol. We know OH is not a good leaving group. And so if we want to take alcohol and turn it to another compound, the first thing that we need to do, we need to replace OH by something else. And if you can turn OH to something, OH with a negative charge to something like, let's say, for example, water that has zero charge, that's going to be a good leaving group. So whatever you do, turn OH to a good leaving group. One, replace it by, for example, halide, and halide, it will be a good leaving group, or turn it to water, and water is going to leave the system. Okay. We have a couple of methods for this purpose. One of them is going to be the thionyl chloride, and this compound is going to give is going to replace the OH by chloride. So this is the OH, it will be replaced by chloride. And what do we have here? We have a sulfur that attached to chloride, and one oxygen is a dichloride, the chlorose sulfoxide. And the next one, mainly we call it thionyl chloride. And next one, it says PY. That's a pyridine compound. It will behave as a base. Why? Because nitrogen has a lone pair, and then nitrogen, it can have interaction with hydrogen. And if that case happen, then this one, it will get a positive charge. So it can behave as a base. And another chemical compound that we can use is phosphorus tribromide. And instead of chloride, this time it will tag the compound by bromide. It will attach bromide instead of OH, and we get this type of product technically. So wherever we have OH, if we use thionyl chloride, wherever we have OH, we will get chloride. And if we go with PBr3, in that case, we will get bromide. Okay, I want to go after one of this chemical reaction and show you the mechanism for it. And so let's say we are going to go after the second chemical reaction. And the second chemical reaction, it says we have this alcohol. So we have O there attached to hydrogen. Oxygen, it has two lone pairs. Okay, and next I'm going to say I have phosphorus, and phosphorus is attached to three bromines. Okay, so phosphorus has sp and d orbital. That means it's capable of actually forming more than 4 bonds. It can have 5 bonds easily. And in order to do it, it will actually use d orbital to make more than 4 bonds. And so what will happen in this case? We have bromides that each one, it has three lone pairs. And while oxygen is attacking the phosphorus, bromide, one of this bromide will take the 2 electrons and it will leave the system. So what do we get on the product side? We get this oxygen attached to hydrogen, and it has a lone pair, but it's going to have a positive charge. And this one, it will be attached to phosphorus, and phosphorus still is attached to 2 bromines. And each bromine, it has 3 lone pairs. Plus, we get one, like another product, and that product, it will be the bromide. Okay, bromide, it will have 4 lone pairs, so that means it's going to have -1 charge. Okay, now look to oxygen. Oxygen, it has a positive charge. Oxygen is really electronegative. Oxygen does not want to have actually a positive charge. So oxygen, it will do this. It will try to steal these 2 electrons and leave the system. And if the oxygen leaves the system with those 2 electrons, it will be neutral. And bromide is going to use this actually condition or this situation, and it will attack carbon. And if attack that carbon, we will get this product. So next step of the chemical reaction, we will have SN2 reaction. In our nucleophile, it will be the bromide. And the bromide will go after carbon, and it will be inserted to carbon there. And OH will leave the system. And in that case, we will have hydrogen attached to oxygen. Oxygen now has 2 lone pairs and is attached to phosphorus, and phosphorus attached to 2 bromines. Again, each bromine has 3 lone pairs. And so one of the product, it will be alkyl halide, and our X in this case is going to be a bromide, and the second one, it will be HOPBr2. Okay, and so as you see, we got alkyl halide, and we started with a primary alcohol, and we ended with an alkyl halide. And also we got an acid, and our acid is not that strong acid, but still it has some acidic character. what will happen if you expose alcohol to acidic situation? And also, let's say you are adding heat to the system. In that case, the elimination reaction very soon start to be the dominant mechanism. And remember, we are using acid. If you use an acid, let's say HX is going to turn to H plus and X minus. X minus, it will be the conjugate base. So for example, if we go with H2SO4, we get H plus and HSO4 minus 1. This is going to be the conjugate base. Okay. Now, first step of this reaction, oxygen that has two lone pair, very soon it's going to get one H from the acidic solution, and it will turn to species with a positive charge. Okay, oxygen is not going to be happy, so oxygen, it will try to steal those two electrons and leave a carbocation, leave the system with a positive charge, or technically a carbocation. We started with a tertiary alcohol, so that tertiary alcohol is capable of accommodating a positive charge, and it will give us a tertiary carbocation. A tertiary carbocation can easily handle the positive charge, and remember, we do have hydrogens on those methyls, and those hydrogen, if they see, okay, if they see in like a base, they might have interaction with it, okay? And that's going to give us an elimination product. Why this one can happen? Because a hybridization for this carbon right now is sp2, and sp2 is too electronegative. What does it mean? It means it's going to pull too much, electron density to itself, and it will leave a good positive charge on hydrogen. So those hydrogen are going to have a huge positive charge. It means they are more acidic. And what's the base here? Our base is going to be HSO4 minus 1. That's going to be the base. The base is going to go after one of this hydrogen, and it will take it after the system, and we will get such a product. Okay, now we got a double bond there, and this one gave us an alkene. Okay, now what will happen if we have more than one beta hydrogen? Okay, so in the previous example, we had only one type of beta carbon, and we ended with only one type of product. And in this case, this is the alpha carbon, the carbon that it has the OH, and I have beta 1 here. That's going to be beta 1. Those two are identical. And also we have beta 2. Okay, so we have two types of hydrogen there. And again, first step of this reaction is, we'll get the hydrogen attached to OH, and it will give us a carbocation. So straight, I'm going to draw the carbocation. I get this one here, carbocation, and because this is a tertiary carbon, it can easily handle the positive charge. Next step, our base, it can take hydrogen from here, this one, or that. Okay, let's call this one 1, and that one 2. Okay, if we go after any of the beta 1 hydrogens, and the product will be something like this. So if we go after beta 1, product, it will be this. Okay. And if we go after beta 2, then the product will be this compound. And remember, the one with more substituent, it will be more stable, and that's going to be the product. And this one, it will be the half-man product. Okay. So we get two products. Which one is more stable? The Zaitsev product is more stable, thermodynamically more stable. So this one, it will be the major one, and this is going to be the minor product. And I'm going to stop the lecture here, and thank you very much.